All right. We are going to do some example problems now. These will be similar to the example problems that'll be on your quiz that's due next week. So, might be a good idea to pay attention. Or not, I don't tell you what to do. Oh, FYI, taking notes is a great idea. I have had some students sit in this class and not take notes. They got terrible grades. I'm like, why didn't you take notes? Well, I don't ever take notes. Like, well, you better learn how to do that because they're in college. I just saw that on YouTube, nice. All right, so when it comes to Kirchoff's laws, we need, how do we use this? Well, we're gonna start with an example. All right, so what we have here is a DC circuit. And what we'll do is we will start with a fairly simple system. Okay, we're gonna call this VS. This is gonna be R1, this is gonna be R2, this is gonna be R3. Okay, nothing too shocking yet. A couple of scribbles on a board. Now, what we'll have is the current going through this component, we'll call this IR2. The current through this component, we'll call it IR3. The current through this component, we'll call it IR1. Okay, now I did draw the currents all in very specific directions. You'll notice at the positive end here, this is actually the positive end of the resistor, this is the negative end. Current flows from the positive end to the negative end. That shouldn't be anything shocking to you. Again, here's the positive end, here's the negative end, here's the positive end, here's the negative end. You'll notice the negative end is connected to the positive ends of these two resistors. The negative ends of the resistors are connected to the negative end of the battery. Okay? When we say, in Kirchoff's voltage law, when we say that a component is negative, it's because as you flow, the current IS goes from the negative end to the positive end. That's the whole reason why it's called negative, is because it goes from negative to positive, whereas in every other passive component, it's going from positive to negative. So just a decision there for how to distinguish them, okay? Well, not everybody can be positive. Okay, now what we'll also do here is we'll start with identifying KVL first, okay? When we do KVL, what we have to do is we have to figure out what loops are present, okay? What is a loop? It's a completely closed circuit. A totally closed path, okay? Do we have any loops? Yeah, we're going to have a couple at least, right?
We have to add the R2 and R3, no?
We do have, so one loop here is actually this one, yes. What other loops do we have?
The other one.
The other one.
And the third one.
And then you can't have the third one, which is all the way around. Okay? There's only 3 ways of drawing loops in this circuit. Okay, so all current that goes through this loop, all current that goes through that loop, and all current that goes through this loop. What we have here is we can now write out our KVL equations. Okay, so what is the KVL equation? Sum of the voltages in a loop is equal to 0. So when we write out our KVL equations, we're going to go ahead and number our loops. I'm going to call this one loop 1. I'm going to call this one loop 2. I'm going to call this one loop 3. Okay? So, for loop 1, what is the what all voltages are present in loop 1? Here, this is, so we got Vs, okay? What other voltages are present? R1 and R2. Now you'll notice I didn't put any signs on these. Again, it's considered positive if it goes from the positive end to the negative end. So as we go around this loop, this is considered negative because it goes, as the current goes through, we're traveling on the current train, it goes to the negative end of the component and then goes to the positive end. So it's considered to be negative. It's current imparting, it's a voltage imparting component, it's a source, okay? And then as we continue this current train, we then come to the positive end of R1. Then we travel to the negative end of R1, which means that this is a positive component. We then continue around this loop. We come to the positive end of R2. We then go to the negative end of R2, which means that is a positive. And then we continue this current train all the way back to the start. Okay, so that's our first equation. Negative Vs plus R1 plus R2 is equal to 0. Now I did say another way of writing this is you can write it as voltage in equals voltage out. Yes, you can do that.
So it's like statics for circuits.
Pretty much. It turns out actually that all physics share a number of equations that are similar because calculus is the same for all of them. Yeah.
It depends how they add together the resistance, they are in series or parallel.
We will get into the difference between that yet. For this one, we're only looking at this one loop.
It doesn't matter in this way.
In this one, it doesn't, not yet, yeah. That will matter more, but it'll show up in other ways. We'll actually get into that next week, but yes. So, voltage in equals voltage out. We could just rewrite this equation as VR1 plus VR2. Oh, I should have written this as V instead of just R1, R2. VR1 plus VR2 is equal to Vs, okay? So we can, that's the same way of writing the exact same equation. I just moved the negative from this side over here. Nothing too shocking yet. Let's go ahead and do it for loop 2, okay? So in loop 2, what components do we have? So we've got VR2 and VR3. Now, we don't have a battery in this loop. There is no battery in this loop at all. Yeah. We do have a current, yes. And the current, what we're going to do again is we're going to consider the current to be clockwise, to be positive. So here, when we go through R2 clockwise, we go through in the negative direction and come out the positive direction. That actually makes this a negative. Okay? Yeah, it's dumb, but that's sign conventions here. And then we go around this, we go into the positive end of R3, come out the negative end. That makes this a positive. Since those are the only components, comes out as 0. Another way of writing this is that VR2 is equal to VR3. By the way, these components are in parallel, which is why VR2 is equal to VR3. But again, we're not going to get into that until next week. So we're introducing the concepts, and then we'll step back, and then we'll step forward. I like to make things confusing. All right, let's now look at loop 3. In loop 3, what components do we have? We got Vs, we got VR1, and we got VR3. Okay? Now, as we go around the loop, we come to the negative end of Vs, we come out the positive end, that makes this a negative. We come to the positive end of R1, we come out the negative end, that makes this a positive. And then we come to the positive end of VR3, and we come out the negative end, which makes that one. We can rewrite this equation using this to say that VR1 plus VR3 is equal to Vs. Now, something I would like you to note. If we only took these two equations for loop 1 and loop 2, we can derive loop 3 equation. Because if you just take this piece right here and plug it in right here, you've got this. So we really only have two different equations that have been generated here. It turns out when you have your node equations and your loop equations, you end up generating the number of those loops minus 1 equations out of your system. So, and you can actually have fewer loop equations than this depending on how creatively you can draw your loops. But that's a different story. Okay, so now let's do KCL. Okay, what is KCL again? Can you say that again? Current in equals current out. Okay, so if we have any nodes in this system, the amount of current that goes into that node is equal to the amount of current that goes out of that node. We don't lose any electrons anywhere in the system. All right, so that means we have to identify nodes. I'm going to go ahead and show you where I would identify nodes. Here, as we talked about earlier, this node is going to start from the end of this component and go over here. This node, we'll talk about that too. And then I'm going to draw a node over here. So this will be 1, this will be 2, this will be 3. Do we have any more nodes? The answer to that is no.
No.
Thanks, Jeremy. The idea here is that everything that is connected to node 3 that has the same voltage as node 3 is going to be considered to be part of this node. So node 3 extends from here all the way up to here, all the way up to here. So I could have written node 3 here and it would have been the same. I could have written node 3 right here and it would have been the same. All of them are at the same voltage because there's no components between any of those points. I can draw a straight line from each of these points directly into node 3 without going through any components. Therefore, they're all part of the same node. Okay? We got to keep that in mind. If you have too many nodes, it starts making your equations look weird, and you can make some really bad mistakes. All right. What's our equation for KCL? You already said it once, I'll just write it. We have the currents in is equal to the current out. Or we could do the sum of all currents into a node is equal to 0. Well, either of those work. They're the same equations. So what we'll do is we will look at every single node. We'll start with 1. All right. What currents are going into node 1? We have IS. I signifying that it's a current. Do we have any other currents going into node 1? Now it's coming out of node 1. So I'll put it on the other side, yeah. Do we have any other nodes, any other currents that are even touching node 1? No. So this is the equation. It really doesn't get any more simple than that. Okay. All right, so what about the next piece? Node 2. Now, once again, any piece on this line, if I were to draw a line between it and node 2, there's no components in the way. They would all be considered part of node 2. So, what currents are going into node 2? We got IR1 again. Do we have any other currents going into node 2? This is IR1. All right, what currents are going out of node 2? I'm leaving. IR2.
It's not leaving right there.
Yeah, it is.
No, it's leaving all the way up the other part.
Yeah, but it's leaving to leave.
And it's still traveling the node right there.
Yeah, it's traveling the node, but it's trying to get out. And it's like terminal. And then this is IR2. Okay, so we can write all of them here. IR2 plus IR3. That's node 2. Okay, what about node 3? What currents are going into node 3? We have this component here, this component here. So IR2 plus IR3. What currents are going out of node 3? Is equal to IS. Now once again, what you'll notice is we can take the first two equations and derive the last equation. So we only really have the number of nodes minus 1 equations that we generate that are independent here. Independent meaning that we could create a basis for a system out of it, but it's just what we found. All right, any questions on this? We're working on, first week, already starting to derive some of the equations that we're going to be needing in this system. Okay? All right, let's do it again. This time it's on you. Oh no, we'll do another hard one and then I'll give you one, okay? So that was kind of an easy circuit to work with for first time around. You'll notice there's a lot of labeling that we have to do in order to calculate these circuits. Okay? Let's work with actual numbers this time. All right. Now this is what's going to be called, what I drew last was a voltage source. What ends up happening in a voltage source is it has a variable current depending on the system. This is called a current source. It has a constant current but a variable voltage depending on the system that it's connected to. Okay? Merry Christmas. We'll call this R1. We'll call this R2. This will be R3. This will be R4. And this will be R5. Starting with a fun circuit. Okay. Gross. Go ahead and try. If you draw it wrong, you're wrong. All right, bet. What's up, bro?
What's up?
How's life? Oh, I made it too easy.
Yeah. Now I'm gonna do this.
That's correct. Nice work. Until I change it. No, I'm not going to change it. I'm kidding. All right. So this is now gross. Unless you do it Jeremy's way, in which case then it's less gross. Monster. We'll start with KVL. When we do KVL, the thing that we have to identify is loops, okay? There are a million different loops that we can draw in this system. Let's be honest here. Are you talking to yourself?
I think we have 5.
There are a million different loops you can draw in the system. As a general rule of thumb in circuits, the way that you're supposed to identify loops is in what's called panes, which means a loop is a space that is enclosed. You know, it's like if you've ever done the box drawing game, that's basically how we're going to identify loops. So this is going to be one loop, this is going to be one loop, and this is going to be one loop. I always struggle with talking because I just shout when I teach. So at the beginning of every semester, I'm just dying. Doesn't help that I've been sick, but whatever. So here, we're only going to have 3 loops that we really talk about, okay? Some of these loops do share components, but because we're drawing these loops in this way, we're actually not going to have any redundant equations. We'll call this loop 1, we'll call this loop 2, we'll call this loop 3. Okay? Before we do that, too, let's go ahead and try to identify positive and negative ends for components. Yeah?
Why we don't have a big loop around the system, like last time?
Because if we were to draw that, it would create a bunch of equations that are unnecessary. So all I'm doing is I'm taking what's panes, which are enclosed spaces, and I'm only defining the loops as those, so that way we don't have too many equations. It should simplify life for all of us, hopefully. Okay, let's identify positive and negative ends for components here before we continue on, because that'll help us out with KVL. So the positive, negative end, is it going to be top or bottom for R1?
I'll say probably on top.
What happens if you get that wrong?
Is it just like standard?
It is just like statics. What you'll find out is that you'll get a negative value for that number. Okay? So if you identify positive and negative as wrong, you'll get a negative value for it, and it just means your current is flowing the wrong directions to that component. Okay? What about R2? Is it going to be top left, or is it going to be bottom right positive? Top left. And then we'll do a negative down there. What about R3? Positive on the left or right? Okay, once again, if you get these wrong, it doesn't matter that much. We're initiating numbers because by drawing positive and negatives, it'll make sure that when we go to do KVL and KCL, we get our numbers correct. All that matters is that you're consistent. Okay? The way I teach all of my classes, number signs suck, but as long as you're consistent about them, we're in a good place. All right, what about R4? Left or right positive? Okay, what about 5, top or bottom? All right, so we'll take those sign conventions and we'll go ahead and build our 3 loop equations. Okay, so we got loop 1 inside of pane 1. What components touch loop 1? R1 and R2. Okay, now remember when we do a loop, we go clockwise around that loop. So when we go clockwise, which end of R1 are we running into, the negative or positive end? Which means, is it going to be positive or negative? This one's going to show up as a minus sign. What about R2? Does it touch a positive or the negative end? It touches the positive end, which means this is a positive component. So here we can say, oops, VR1 is equal to VR2. Okay, what about loop 2? What components do we have that touch loop 2? R2, R3, and the source, right? So we'll have VR2, VR3, V source. Okay, what about R2? If we go clockwise around this loop, does it touch the positive end or the negative end? Touches the negative end, which makes it negative. If we go clockwise around that loop, does it touch the positive end or the negative end of R3? And then what about VS? I guess we didn't really write the negative and the positive end, but it touches the positive end, which means this is actually, according to the configuration that we have, considered positive by going around clockwise. Now we could have flipped all three of these, done them the normal way, just by drawing it a different way. And then we would have ended up with this a negative, these two positive, which is what we're used to. Yes, you can do that, Jeremy. That's perfectly valid. But you have to get the right equations. So we can rewrite this one as VS is equal to VR2 plus VR3. Now, for the third loop equation. What components touch loop 3? We have VS, VR4, and VR5. Okay, as we go around clockwise, does it touch the positive or the negative end of the source? Touches the negative end, which makes this a negative component. Does it touch the positive or the negative end of R4? And does it touch the positive end or the negative end of R5? There we go. So we have our third equation. This is VS is equal to VR4 plus VR5. Now what you will notice here is that all three of these equations are in fact unique. Just by the way that we drew the loops. Yes, we didn't draw the one that goes all the way around. We also didn't draw the one that goes around over here, skipping the source that includes that one. Yes, I know we ignored them, but the way that we drew them, we only get 3 unique loops. So with our 3 unique loops here, we have our 3 unique equations. Okay? Now it's time to do KCL. Now, yeah.
So if we get like VS equals VR2 minus VR3, then we wrote VR3 backwards?
Probably, yeah. And what you would see here is let's take R3 and just flip it around here. Okay? We'll say that we accidentally wrote it backwards. Okay? What you'd end up with here is, as we go around, this would come in as a negative component, this would come in as a negative component, this would come in as a positive, no, this would come in as a negative component, this is a positive, that's a negative. So what you would see here is this would switch, and then we would end up with this negative sign here. And then, yeah, nothing else touches R3, so you would just end up with this one negative, and that would just tell you, like, okay, if you get a value for that, it's probably not negative. But we could also do that for, like, say here we have R2. If we flip R2 around, so I'm going to put this back to where it was. If we flip R2 around, what's going to happen is we're going to end up with 2 equations that shift. Every time we put in R2, it's going to switch. This will be a negative, and then this will be a positive. So then this will be a negative, and this will be a negative. And you can get the same number. As long as you're consistent, that's what matters most. Okay. Any other questions on this diagram?
You always draw those loops clockwise.
I mean, usually. If you draw it counterclockwise, you get the same answer. It's just multiplying this equation by -1. It's just convention is you do it clockwise. Good questions. Our first week, you guys are starting to kick butt already. All right, for KCL, when we started KVL, the first thing we had to do was identify loops, okay? And we also had to identify like what directions we wanted components to be labeled as too. But we needed to do that no matter what. The first thing we have to do with KCL is we have to identify nodes. So here, first thing we had to do is identify loops. Here, first thing you have to do is identify nodes. Okay? It'll be same both ways. What I'm going to do here is, again, I'm going to identify the nodes because I want to show you how I would do it. It doesn't matter which node is number 1. It doesn't. I like to make node 1 the first node after the source voltage, because then node 1 has the highest voltage. But it doesn't really matter otherwise. And then you just start drawing other places. Here, this collection, I'm going to call it node 2. This piece down here is node 3. Node 3. Huh?
So which would be 4? Just go R4, R5, and then it leads into and they all combine.
I'm ignoring you.
Okay, I made the same mistake.
Don't make the mistakes I do. Here, node 3 goes from the bottom of R1, connects to R2, connects to the bottom of the source, and also connects to node 5. There are no components in that line at any point, so they're all at the same voltage. Okay? And now we really only have 4 distinct nodes here. So that's fun. Awesome. All right, so we'll do first equation for node 1. What currents are going into node 1? What currents are going out of node 1? There we go. And here, we can notice that the current direction here goes from positive to negative. Here, we assume that it goes from negative to positive, which is why it's a source component. But for everything that isn't a source component, we just assume it goes from positive to negative. Okay? What you would find out here is if you wrote these backward, your currents would also be facing backwards, which is fine, but you just have to make sure, again, you stay consistent. These equations and these equations have to be in the same basis. All right. What currents are going into node 2? IR3. What else? Is that it? Yep. All the other currents are pointed away. So then what are coming out of node 2? Okay. What about node 3? What currents are going into node 3? IR1, IR2, and IR5. What currents are going out of node 3? Oh, yes. And then node 4. What currents are going into node 4? And what currents are coming out of node 4? Okay, now once again you'll notice here, one of these equations can actually be derived from the others. Here, if we take these 3 equations and combine them together, we actually do get that IR4 is equal to IR5. That's just the nature of how node equations work. We're not going to write one less node equation. We can only really simplify the loop equations to make sure that they aren't unique. So what I'm going to do is I'm going to give you an equation. I'm going to give you a system, and then Sam, you and Hyunjin have to go, right? Yeah, I'm going to give you an a problem, and then I'll show you the end of it at the next video that I post online. So, third video from today. Yeah.
Can we go through where we got node 3 again?
Yes. Okay. So, for node 3, the way that we have is we have this current that's running from positive to negative in R1. Okay? It goes into node 3. Node 3, we could call this, like node 5. We could call this node 6, but really there's no component that separates them. So 3 is equal to 5 is equal to 6. So here, anything that comes in to 5 will be also coming into 3. I know that seems a little counterintuitive, but it's just how, because it's all one node. Does that help?
Yeah, that helps a lot.
Okay. Yeah, the problem with doing it with writing like this is node 5, this is node 6, is that now the current coming out of node 3 goes into node 5. It just makes it harder for me to understand. But yeah. So all of these are coming in. And the beauty of that is, as Jeremy pointed out, you can actually redraw your system such that you could make all of these one point. And yes, you can. You have the ability to do that. It's gross. You actually have to curve lines to make it happen. But you can, and if you do that, great. But you can redraw it. And that's why I like to keep it at one node. All right, so I'll give you an example problem for you to work out yourselves. I'm going to shut off the live stream, and I'm going to show you the example to this in the next lecture. Just watch this in your own time. And then you guys can go to Joel's class. No, it's, they've got senior design. You'll have it next year. Well, it's not bad. By that point, you'll already have been huh? Yeah. Yes, you start on senior design at the end of your junior year. Yeah, we like to keep you working on projects all the way until you graduate.
Makes sense.
It does. It started.
Job after graduation is project.
Yeah. And projects are the most fun part, in my opinion. But, okay, so here's the example problem of what I'm giving you. Okay, so this will be R1, this will be R2, R3, R4, R5, and R6. And yeah, you've got to assign loops, nodes, directions on your own, okay? So I'm going to turn this over to you guys, and then you can draw it however you want.